today is the 3043 stuff. This is your calculations on thermochemistry, and it does involve some explanations. The maths is fairly simple. You use Hess's law and you use calorimetry. And then we're also going to touch on those definitions I finished off last week. In fact, we're going to start with those because you need these for those equations. So if you think of, remember there were 5 or 6 definitions you needed to know. By definitions, I mean the thermochemical definitions. So for instance, the heat of formation. So if you're given a delta FH, then you know you must write an equation where you've got 1 mole of that substance being formed, so it's 1 mole over here, and it has to be formed from its elements. So you can only have elements on the left-hand side and 1 substance on the right-hand side. So when you balance it, you may need a half or something like this. So if I wanted carbon monoxide, I would have carbon monoxide on the right-hand side, CO. I'd have C on the left-hand side, and the standard state for carbon is always graphite, because remember you've got different allotropes of carbon. Do you know what I mean when I say allotrope? Yep. Okay, so it's an element in different states. Okay, allotrope is the atoms of an element can actually bond in different ways and result in different structures. So for instance, carbon can either be a diamond structure, or it can be graphite, or it can be like buckyballs or nanotubes or graphene. So those are all different ways the carbon atoms combine, and so the properties of those substances will be different. So not every element can have different allotropes, but a lot of them can. So the allotrope we pick is always the one that's at the standard state at that temperature of 25 degrees. So it'll be graphite rather than diamond. So for carbon monoxide, you'd have CO on this side, C over here, and then of course to balance the O2, if I've only got 1 oxygen on the right-hand side, what must I put in front of O2 to make it balanced? So my unbalanced equation is C plus O2 goes to CO. How do I balance it? A half, 0.5, correct. I don't try and say 2 carbons plus O2 goes to 2 CO, because I can only have a 1 mole of the substance on the right-hand side, so I have to put a half in front of O2. Okay, so that's the heat of formation. Heat of reaction is always as given, so we normally would give you the reaction and say work out its heat of reaction. Or we'd give you the reaction, give you the heat of reaction for you to work out for another given reaction, some sort of thing. So it's always as written. So for instance, a value that's associated with this, if we give you a value, it's for this as written: 1 mole of N2, 3 moles of H2, and 2 moles of ammonia. Okay, heat of combustion is always 1 mole of the substance on the left-hand side reacting with oxygen to form the usual products on complete combustion. So if it's a hydrocarbon like octane or methane or something like that, it's always carbon dioxide and water. This is an example also of a combustion reaction, but the combustion of sulfur. So sulfur burning an oxygen to give SO2. If I was burning carbon, what would be my product on the right-hand side? Because it'll be carbon plus oxygen. What would I form? What would be the most normal one for complete combustion? Carbon dioxide, correct. You wouldn't say carbon monoxide because that's not complete combustion. It's to where it's totally gone. Okay, then remember there's the heat of fusion, there's the heat of vaporization, and then also the heat of sublimation. Now these ones you can get questions in the exams also relating to your intermolecular forces and not just under calculations in chemistry. So just bear that in mind, and we'll look at some examples. So using definitions, this is when we try and work out heats of reactions or heats of formations and so on. So you will be perhaps given a delta RH or a delta FH and so on, and then you must be able to write the equation relating to it and then work further with that. So what I'm trying to show here is if my energy of reactants is lower than my energy of products, then I've got what sort of reaction, exothermic or endothermic? Abigail, I'll answer your question just now. So if my energy of reactants is lower than my products, is it exothermic or endothermic? It's actually endo, okay, because I've had to add heat from the surroundings to get to a higher energy state up here. So that'll be an endothermic. So although we say heat given off for the reaction is written, it could also be for the heat needing to be added in. Okay, so it's the heat involved. And it's the delta H is the difference in energy between the reactants and the products. Okay, so Abigail, is sulfur dioxide or trioxide the complete combustion? It's actually the sulfur dioxide. That would be the standard one that's being formed. You wouldn't be asked in the exam, you wouldn't be expected to know things, you know, like that you'd expect if I burn anything that you expected to know the product. What they would expect you to know is that if you've got a hydrocarbon of some sort, that you would be forming carbon dioxide and water. That's totally expected for complete combustion, because that's really level 1 chemistry. For the others, there would be clues along the way that you would be able to work it out. So for an example, the one that's in your teacher marked assignment, where we ask you, why is the heat of formation of sulfur dioxide the same as the heat of combustion of sulfur? Well, you know, then you can work out it's exactly the same equation. So you're forming sulfur with oxygen going to sulfur dioxide. Okay. So when we work out the delta HR, then the energy of the products is energy at the end, and we subtract energy that the reactants had to start off with. And that'll be our difference. So it's always products subtract reactants. And this is what we use for Hess's law. So basically Hess's law, and you may be asked as an achieved level question to quote this law. It's pretty much where it doesn't matter which pathway we go from reactants to products, our final difference in energy will always be the difference between our first reactants and our final products. So it's a change of enthalpy in a chemical reaction is independent of the pathway between the initial and final states. So I could have started with some reactants, gone and formed other products, and then other products, and then other products, and then finally these products. So the difference between these products and those is still that same delta H. So here, for instance, if I take methane and I burn it in oxygen, I can go straight to carbon dioxide and water, or I could have done an intermediate step where I could have gone to carbon monoxide, and then the carbon monoxide reacted further to form carbon dioxide. So do you see what I mean? It doesn't matter which way we go, eventually our delta H will be the same difference between the first reactants and the final products. Okay, so you basically work with these equations and you cancel them out until you get the equation you want. So you've got two ways of doing it. You use the short method, where we use that previous equation. So if I go backspace, this one, okay, or you've got the long method, is where you've got to write out those equations. So the short method works best when really everything's in heats of formation. I would use a short method for when everything is given as heats of formation. If there's any heats of reactants and so on, you could start getting into trouble. If you've got more heats of reactants, I would go for this long method. So let's go for example. So here is use the heats of formation information, so we can go, or perhaps I can use a short method, to work out the heat of reactants. But everything is given as a heat of formation. So what we're basically saying is, I know the heat of formation of this, and I know the heat of formation of that, so I know the final energy of my products, and I know the heat of formation of this, and I know the heat of formation of the H2O, so I know the total energy that I started off with. So can you see this is quite easy to subtract? The only difference you've got to do is I've got 2 HCl, so I need twice as much for the HCl energy, and I've got 2 waters, so I need twice as much for the water. So that's pretty much just linking it together. So hopefully you would see that those are the products. And so I just simply substitute, those are the products, those are the reactants. And can you see I've got there the 2 HCl and the 2 water? Because for every molecule where I've got to break bonds, I have to add energy for every molecule I break. Okay. And okay, I'm just highlighting the 2 and the 2 over there, and then you can work it out and you get your final answer. And if it's a negative answer, then you know that the reaction was what? Exothermic or endothermic? Exothermic, and heat was released. So just be very careful when you do your final statement. You can say 62 kilojoules per mole of energy is released, because the released implies a negative. Or if you don't make that statement, make sure that you've got the correct sign. Okay, so even if you, so I'm looking at my cursor, I think they accept it if you said you had negative 62 kilojoules per mole of energy released. It's like a double negative, but they still accept it as being exothermic because you said energy was being released. Okay, so just be aware of the sign, and please, we use kilojoules per mole, because all along we were working per mole. So in any of these reactant things, it's always the unit is kilojoule per mole. That's important for excellence. Any questions on the short method? No? Okay, Caleb, I see there's typing. No. Okay, right, so the Hess's law. So here we have to write out the equations and then check that the equations cancel out correctly, leaving you with the equation you want. So the important thing is make sure the equations are balanced to start off with, because otherwise they're not going to cancel properly. Okay. When you have to reverse the equation, say you wanted some ammonia on the left-hand side, but all the equations are on the right-hand side, then you have to reverse it to make the equation on the left-hand side. And whenever you the ammonia on the left-hand side, and whenever you do reverse the equation, then you reverse the sign. Yes, I enjoy that. You've got to be particular. Students can very easily make a careless mistake, but it's actually a very simple sort of thing. You just have to check all the time. And just like you multiplied that HCl and H2O by 2, the same thing here. If I've got 2 HCl in, needed, or twice that equation needed, then you multiply the delta H by 2. Now, as a tip to help you work out the cancelling, so what's a product and what's a reactant, draw always your arrows down the middle of the page and then squeeze in your reactants on the left-hand side and your products on the right-hand side. Don't make it if you've got lots of reactants and then have the arrow far on the right on your page, and then if your next equation is that the arrow is, you've only had one reactant, so the arrows far to the left, then you're going to get yourself confused when you cancel. So always just draw all your arrows down the middle of the page and then fit in your reactants and products. And then double check your calculations. I always say do your calculations twice, because you never know when you made a mistake. And then, of course, your unit for these type of calculations is always kilojoules per mole. Calorimetry, it can be different. It's either kilojoules or kilojoules per mole, depending on what they ask for. But in these type, it's kilojoules per mole. So here's an example. So basically, they're saying, I've got this reaction over here of NO burning an oxygen to form NO2. Okay, and then you've got to work out what that heat of reaction is. What I'm given are two, well, they're not really heats of formation. It's a heat of reaction because the 2 is there. This you could say is a heat of formation, but it's also delta. Delta RH is the default thing because it's always the heat of the reaction regardless. So if that is my given reaction that I've got to work out, you just look what's on the left hand side and what's on the right hand side. I need NO2 on the right hand side, and I need NO and oxygen on the left hand side. So always start off with the most complicated molecules in the first place. So NO2 is on the right hand side here. So you look at these equations and you see, aha, NO2 is on the right hand side here. But what is in this equation that's not in this equation down here? What is missing? A 2. So I need to double this equation down here. So it'll be 1N plus 2O2 goes to 2NO2. And of course I have to then double this 33 kilojoules per mole. Okay, so that's just sort of showing what you've got to do. The NO, I've got 2 NOs, I've got 2 NOs there. Now, I've got the same amount of NOs, but they're on the wrong side. Here, where I want it to be is on the left-hand side. Where I'm given, it's on the right-hand side, which means I have to get this onto the left-hand side, so I have to reverse the equation, which means I have to reverse the sign. Okay, and oxygen is all on the left-hand side over here. When we reverse, it'll change, but we'll just leave that last. Okay, so let's look at that one first, and I've reversed it because I wanted the NO2 on the left-hand side, sorry, the NO on the left-hand side. Do you notice I've kept all my arrows below each other, so I can easily cancel this one with that one. Okay, and notice I've changed the sign. It was positive, it's now negative. Then this one I have to multiply by 2. So I've got the 2 in front, okay, and so I've had to multiply the 33 by 2 to get 66. Now we start the cancelling. So my N2 cancels out with that N2. Now the 2 times a half is the same as 1. So I've got 1 N2 on the left-hand side and 1 N2 on the right-hand side. I've got 2 O2s on the left-hand side and 1 of them on the right-hand side. So I'm going to be left with 1 of them on the left-hand side. And then, and that's it. So now I can just put down my uncancelled stuff. 2NO plus my uncancelled oxygen plus my uncancelled NO2. And that matches my equation. So now I just work with the sum. Minus 183 plus 66 gives me minus 117 kilojoules per mole. So this is where we gave you all the reactions. Normally in the exam they just say the heat of formation of NO or the heat of combustion of N2 or something like that. So the tricky part with Hess's law is that you've got to know your definitions so that you can write the equations to do to work it out. So here's an example where I haven't given you the equations. I've given you the final one that I want you to work out. Oh, hang on. I've asked you to work out the delta, the heat of formation of hexane. I've given you 2 other heats of formations plus a heat of reaction. So now just very quickly going through it, you would say, what is the equation I'm aiming for? So can I write the heat of formation of hexane? So it's one hexane molecule on the right-hand side and carbon and hydrogen only on the left-hand side. Okay, so these are my 6 carbons, 7 hydrogen gases, because it's always in the standard state to form my hexane. Then you just write your other ones down, okay, from the given data. So my heat of formation of carbon dioxide is carbon with oxygen. The heat of formation of water, okay, is half O2 plus H2 goes to H2O. And I should have aligned my arrows, but anyway, we'll now manipulate them. So we've got this equation up here, plus the 2 we've written to work out our final equation that we want. So we want hexane on the right-hand side and hydrogen and graphite on the left-hand side. So if we look over here, we've got hexane on the left-hand side, we want it on the right-hand side. So what do we need to do this to this top equation? We reverse it, and then we reverse the sign so it becomes positive. So we basically say we need 6 of those, we need to reverse that one. The 6 is because I need 6 carbons, and this is the only equation that gives me carbon. And for this one, we need 7 of these because I need 7 H2s, and this is the only equation that gives me H2. So starting off with that, I've put it down here, and here's my 6 times that value that we were given. Okay, then this one, if I put it down here, keeping my arrows aligned, it's 7 times that value. Okay, always show your working. The reason being, you can still achieve a question if you make a stupid stuff up. So if the examiner can see where you've stuffed up, they can say, okay, still achieve level. But if you just write a mass of numbers without showing really your method properly, they won't bother trying to work out where you went wrong, and then they'll say not achieved. So always make sure you show your working very clearly. Then the top one up there, bring that one down, and we reverse it and keep your arrows under each other. Now we just cancel. So the 6 O2s go with 6 CO2s with those CO2s, the H2Os cancel the H2Os, and then the oxygens cancel out with those oxygens plus those is 9.5, and we left them with graphite, hydrogen, and hexane. So we just take it all down. So if you've got it properly aligned, you're less likely to make a stupid mistake and put it on the wrong side of the equation. And now you just basically say that plus this, and remember a negative times a negative is a positive, and it'll give you that answer. So do you think you should be able to follow Hess's law? Okay, there is an interactive, whoops, there's this one over here, and I'll put this up on the Ottel News, so you can manipulate these equations any way you like by bringing them in. So if I've just got that, this is just my final one, but if I put that one there and I reverse that, then that'll be the final one. And can you see how the delta H changes? So you can play around with this and see what you come up with your final one, depending on if you're reversing or clearing, or you might want to have something else on there, and so on. So that's for you to play around with, just to check that you've understood it. Okay, coming back to this one from current slide. Okay, that's example 2. I'm going to actually go a bit okay, hang on, I'm going to just, sorry, I'm going to go back here. So here's what came up in the 2015 paper. So you've got a given equation, and you asked for the combustion of pentan 1-ol, and hopefully you can see this is a heat of combustion. Okay, so you recognize that, and then you're given the heats of formation. Now, as I say, if you've got the heats of formation, you can use the short method. So pretty much I've just used the short method here because they were all given as heats of formation. So we're basically saying the heat of combustion is 5 times the carbon dioxide, so 5 times this one, 6 times this one, subtract my formation of pentanol, sorry I went blank there, and subtract my oxygen. Now notice with my oxygen, if the definition is for a heat of formation is the substance, 1 mole of the substance and then formed from its elements in the standard state, if I'm forming oxygen gas, it's formed from oxygen gas. Is there any difference between oxygen gas going to oxygen gas? No. So if there's no difference, I've got oxygen gas and it's forming oxygen gas, there's no change in energy. It's still oxygen gas. So if there's no change in energy, we say that the energy is 0. So that's why if you've got any element in its standard state, it could be copper metal, it could be sulfur solid, it could be graphite, carbon graphite, any element in its standard state will always have a heat of formation of 0. So they may not sometimes give you something because they expect you to know it. So here, for instance, you'll notice they did not give you oxygen because they expected you to know that the standard state, you know, of oxygen gas is oxygen gas, so there's no change in energy, so it's 0. And 7.5 times 0 is still 0. So just be aware of that little trick, okay? Because you might go, oh, I can't do this because I'm not given all the information. Okay, that's the way to get around it. Otherwise, do it in the long state. So here was, that was actually sort of achieved level. Hess's law is often a merit level, depending on how tricky they make it, but otherwise it's a merit level question. So here they ask you to calculate a heat of formation. So you can still do this the short method because you've got mainly heats of formation and one different one, but it's a bit more of a tricky one, or you do it the long method. And if you want to know the answer, is you want it like that. So that's pretty much, oh sorry, go back. That's how you would work it out. So this is the long method, but otherwise you could make it a more complicated one where you're solving for the middle. But you know, you can make it more of an algebraic thing. I always like the long method with Hess's law because I think, like Caleb, I always find it fun. Okay, so that is the one type of calculation where you are expected to know your definitions, but otherwise it's pretty simple. The next thing you are expected to know is heating curves, because you are, it doesn't come up very often in the exam. I'd say perhaps every 3rd year or so, but this year could be the year where they're asking about heating curves. So basically you need to know that when you are increasing, you've got a solid that's very ordered, and as I'm adding energy, we're breaking some of those bonds. Okay, well, some of them, but they're basically vibrating more and more and more. Then we get to the point, so if this was ice, then this would be now at 0, because all the energy is now not going into kinetic energy in terms of temperature, it's now going to break bonds. So what we're trying to show here, there it was all ordered, bonds weren't really breaking. Here bonds are breaking, but not necessarily all of them, okay? And it's all that energy we're now adding while we're heating is going to breaking the bonds. Then we've broken quite a few bonds, but it won't be actually all of them. And then we've now got some loose water molecules being able to move around. So if we carry on heating, the water molecules are moving faster and faster and faster, so the kinetic energy is increasing, so the temperature is increasing, until finally we break all the bonds between the water molecules. Now remember, these aren't the covalent HO bonds, these are the intermolecular forces. We have to break them all to separate every single molecule to form the gas. So can you see why the melting point or heat of fusion is lower than the heat of vaporization? It's all to do with the number of bonds. Do I break all the bonds for the heat of fusion? No. I break a good amount of them so that we have some particles separated, but some are still connected, because in a liquid, the particles are actually still very close together, so there's still intermolecular forces. In a gas, the particles are far apart, and they're whizzing around really fast, so there are no intermolecular forces holding them together. We must have added enough energy to have broken all of them. So there is an example of this, and I'll put it again. You can have a look. This bottom one doesn't work, but this top one should. So here is an example. Okay, so you have to mention kinetic energy and therefore the temperature increasing. They are looking always for that, and you've got to say that the temperature is not increasing because the added heat is going to break the intermolecular forces here. So Abigail, in terms of intermolecular forces, there are more intermolecular forces in a solid than in a liquid. That's the difference. Okay, so here's an example, and you can look at it. It's only about a minute, or we're already a bit over, but I'll finish with the heating curves, just to show you that I'm not talking nonsense. A stirring bar and so on would have made this a lot better, because you would have seen a much better increase in temperature. But can you see it's melting? He's heating this. Okay, and it's now, can you see we've got water around the probe, but it's still a bit of ice, so it's not quite as clear cut, because we've still got a lot of ice. So we still, you know, it's not an instant change from ice to liquid. But now, as the ice is pretty much gone, now you can see it's a much clearer increase in temperature. So all this heat that we're adding in here is going into the kinetic energy of the water particles. So it was a bit messy here simply because there was an interim period. And you'll find, as you can see, it's starting to bubble now. So we're forming gases. So can you see it's now going level? Because the energy is used now to break that up. So that's quite a fun thing to look at. Okay, so Abigail, how do you know when something will be a solid or liquid if not observing? Well, they would have to give you some information about that. So you wouldn't be expected just to know that. So they might give you a heating curve and ask you what's happening between A and B, and then you'd go, okay, it's flat, so it's obviously changing from one to the other, and then you just got to see, were you given a boiling point, or were you what were you given? But they shouldn't ever be able to expect you to answer something without you being given the information to process in some way.